Okay, so first one. Okay, they say if f is a function defined by f of x equals. So this is a complex fraction where you kind of have this overall fraction. This is the main fraction bar, and then there's the numerator and there's the denominator, and then in either the numerator or the denominator, in this case the numerator, there's another fraction. Okay, so these are either called I think they either call them compound fractions or extended fractions. One of those two. Okay, for these types, and then they say, here, let's keep going, reading the directions. So they say limit as x approaches 1 is equivalent to which of the following? Okay, so basically, they're just taking limit as x approaches 1 of just basically a different form of this. The only exception is d, but we can eliminate d because limits, if you're taking the limit of a fraction, you can distribute the limit to the top and bottom, which is what they did in d. But you can only do that if the bottom limit doesn't equal 0. So notice if you take the limit of the bottom, that equals 0, and so you can't use the property that limits distribute to fractions if it makes the bottom 0. So can't do d. Okay, so and then look at all the rest. All the rest are just kind of what looks like could be a different form of this. So let's do that. So let's look at a different way to kind of do algebra with this to change the form. Okay, so if you have this overall fraction, okay, so just look at all the different denominators. Okay, notice there's only really one denominator, and that's this x, right? If there were more denominators, you'd find the least common denominator, but there's only one. Okay, so take that denominator and multiply that by the top and bottom. Okay, the top will end up foiling, and the bottom we won't foil, and we'll see why in a second. Okay, so the top will do x times 1 over x, and that's just 1. They kind of cancel, the x and 1 over x cancel to be 1, and then do x times negative 1, or just x times 1 minus x times 1 is x. And then let's keep the bottom the same. Let's not distribute. Okay, now we're going to use like a nice little trick. We're going to use the trick that if you do two things subtracted in the top and then you reverse their subtraction in the bottom, this equals negative 1. And you can test it with numbers. If you do 2 minus 10 over 10 minus 2, right, you get the same thing in the top and bottom, but one's always going to be negative and the other is going to be positive. So that'll always be negative 1. Okay, notice we have that kind of situation where we have two things subtracted in the top and then the same things subtracted in the bottom, but just reversed. So a nice little trick. Those cancel and just put like a negative 1 on the top. Okay, so notice this is really just negative 1 over x. And then now we can see that's a. Okay, and that's a nice thing about limits. If you take limit of an expression, you can like do any kind of canceling and get a simplified version, and the limit, and you can still take the limit of the simplified version, and it'll equal the same thing. So. Okay, next one. Okay, they say let f and g be functions such that limit as x approaches 4 of g of x equals 2, and limit as x approaches 4 of f divided by g equals pi. So what's the limit as x approaches 4 of f of x? Okay, so we'll kind of work off of this one. Let's start with that one. Okay, then we can use the property of limits that they distribute to the top and bottom as long as the bottom's not 0. So we can rewrite this as limit x approaches 4 of f of x. Limit as x approaches 4 of g of x. Okay, just distributing the limit to the top and bottom. Okay, and we should also say that this equals pi. Maybe we'll do it at this point. Right, they say that this limit equals pi. Okay, and then notice that they say limit as x approaches 4 of g of x equals 2. So really this bottom equals 2, and that's really what let us know that we could distribute. The fact that this limit wasn't 0 means that we could actually distribute in the first place. Okay, so let's just rewrite these last two things. This fraction with limits equals pi, but let's substitute 2 for the bottom. So really this is rewrite the top. Okay, and then that bottom is really just 2. Okay, and that's because of this. That equals pi. And then just, bring the 2 over or multiply the 2 over, however you think about it. And now we can see limit as x approaches 4 of f of x is 2 pi. Okay, next one. Okay, they say if f is a function defined above, then limit as x approaches 0 of f of x is what? Okay. So remember when you have a piecewise function and you have a certain function defined for all values of x except a number, and then defined for something else as something else when x equals that number. So basically, really f of x is basically this function for all values of x except for one value. So f of x is basically just that. So let's graph that. Okay, so worth it to memorize, if you have x over absolute value of x like this, or if you have absolute value of x over x like that, same, those have the same graph, those are the same functions. So they look like this. So worth it to memorize, comes up a lot. Okay, so this is f of x, this piecewise function for all values of x except at 0, and then they say it equals 0 at 0. So whenever they say that, they're really just giving you this point, and then we can plot that that's at the origin, really. Okay, and the nice thing is once you graph it, it's a lot easier to find limits. So limit as x approaches 0, we can see it approaches 0 when it approaches 0 from the right. When x approaches 0 from the right, the function approaches 1 because it is 1 the whole time. And the same thing from the left, it approaches -1. And so since they approach different values from the right and left of 0, then this does not exist. Okay, you can just think about if there's a jump discontinuity, if x is approaching 0 and there's a jump discontinuity at 0, then the limit won't exist. Okay, next one says the function f is defined for all x in the interval from 4 to 6. Okay, and really, this is a mistake on this. They really should say is continuous, and there is a difference. Something can be defined without being continuous. This is actually a mistake from College Board. They should say continuous for all x. We'll see why. We'll see why later. Which of the following, it actually doesn't have to be, oh wait, let me think. Yeah, it doesn't have to be continuous at 5, but we should say continuous for all x in the interval. And we should say, whoops, except possibly at x equals 5. All right, we'll see later on why we have to say that. Okay, so this is a mistake from College Board, but that's okay. Okay, so the function f is continuous for all x on the interval from 4 to 6, except maybe it might not be continuous at 5, but it won't matter. Okay, which of the following statements, if true, implies that the limit as x approaches 5 of f of x equals 17? Okay, the first ones don't really make too much sense, A and B. They talk about there exists a function where f is always less than or equal to g. Next one is g is always less than or equal to f. Yeah, we want to know if this statement is true, that it implies that f of x has to equal 17. No, if g of x, if limit as x approaches 5 of g of x equals 17, like in answer choices A and B, and f is above g or below g, it doesn't mean that the limit as x approaches 5 of f has to equal 17. It could really, the limit could be anything below 17 here, and the limit could be anything above 17 in B. So these are just kind of random answer choices. So, okay, let's look at the one C and D down below. So, not always, but anytime that, or a lot of times when you see a triple inequality like this, especially if they're less than or equal to, then you're going to use the squeeze theorem. And the squeeze theorem will, if you're going to use it, it'll always, whatever limit you're trying to show, in this case we're trying to show the limit as x approaches 5 of f of x equals 17, since this limit deals with f of x, then that should be in the middle. Okay, so if this is a squeeze theorem question, it's going to be D, because the limit that we're interested in, the function that we're interested in, is in the middle. So look at kind of the rest of this. So if there exists a function g and h, where g is always less than or equal to f, and h is always greater than or equal to f on this interval from 4 to 6, and the limit of the outside functions equals 17. So they're saying the limit of that one equals 17, and the limit of that one equals 17. Okay, so that's the squeeze theorem. If the function's continuous and this inequality holds, and the limit of the outer ones equal, whatever they equal, the middle one will equal the same thing. And so that's why this has to be true, because the middle one has to equal 17 because the outer ones equal 17. Okay, number 5. Okay, function g is given by g of x equals 7x minus 26 over x minus 5. Function h is given by h of x equals 3x plus 14 over 2x plus 1. If f is a function that satisfies that triple inequality, so maybe we're doing a squeeze theorem again, on the interval from 0 to 5, then what's the limit as x approaches 2 of f of x? So these numbers 0 and 5 don't really matter, except that the x value that x is approaching in the limit, which is 2, is in this interval. That's the most important thing. As long as whatever x is approaching in the limit is in this interval, then we can use the squeeze theorem. Okay, so the squeeze theorem says if we want to evaluate a limit, it has to be in between two other functions, which it is. They say it is. And then the limit of the lower bound function and the limit of the upper bound function as x approaches 2 in this case have to equal each other. If they do, then this limit will equal the same thing. So basically we're just going to find the limit as x approaches 2 of each of those functions. Okay, so here, first thing, always directly substitute. So if you plug in 2 into the top, you get 14 minus 26. Plug in 2 into the bottom, you get 2 minus 5. So that's 4. Okay, this next one, if you plug in 2 into the top, you get 6 plus 14. Plug in 2 to the bottom, you get 5. Okay, so the limit of the outside one is 4, or the lower one is 4, the limit of the upper one is 4. Then that means that the limit of the bigger one is 4. Now, we can only use the squeeze theorem as long as these functions are continuous on an interval around 2. Like if they weren't, so these are continuous. So this one's just not continuous at 5, but that's like far away from 2. As long as the function like exists close to 2, then you can use a squeeze theorem as long as it's continuous. But okay, so whatever the limit of the outside ones equals, then the inside one f of x equals the same thing. Okay, I think this is the last squeeze theorem type question. So definitely when you see 3 graphs and kind of one looks like it's like sandwiched in between the other 2, this is a definite squeeze theorem question. Okay, they say let f be a function of x. The value, the value of limit as x approaches a of f of x can be found using the squeeze theorem with the functions g and h. Which of the following could be the graphs of f, g, and h? So we'll just go right to the answer choice. So answer choice is D. Okay, and the reason why it's D is because we want to evaluate limit as x approaches a of f of x. And so in order to do that, using the squeeze theorem, 3 things have to happen. First off, f has to be continuous, and all these functions have to be continuous, which they are. Maybe not at a, they could have a hole at a, but besides that, they have to be continuous, kind of around a, and that's true. Then f has to be greater than one function, so notice f, on this whole interval, f is greater than or equal to g, right? G is just below f, maybe equal to. Okay, and then now you have also an upper bound function to f. So this function h is above, greater than f of x on this whole interval around a. So you've got a lower bound function to f, an upper bound function to f, and then they all meet at a. There could be a hole here, and that would be fine, but in this case there's a point. And so as long as you've got an upper and lower bound function and f goes in between them and they meet at this point, then you can use the squeeze theorem. Okay, so that's D. Okay, which of the following could be the graphs of f in order to use a squeeze theorem? Graphs of f, g, and h, and that's D. Okay, next one, number 7. Okay, the table above gives selected values for function f. Based on the data in the table, which of the following could not be the graph of f on the interval from 1.9 to 2.1? Okay, so all the answer choices actually go from 1.9 to 2.1 almost exclusively. Okay. So, and look at all the differences. This one's continuous at 2. This one has a removable discontinuity at 2. This one has a removable discontinuity at 2, but it's defined somewhere else. And then this has a jump discontinuity. And they say, which of the following could not be the graph? Okay, so let's look around what's happening at 2. Okay, so looks like when x is approaching 2 from the left, it looks like the function's decreasing and approaching 3. And then it looks like when x is approaching 2 from the right, looks like it's also approaching 3. And you can see the function is decreasing. I guess they're all decreasing. Okay. So really, this suggests that when x approaches 2 from the left or right, the function approaches 3 from both sides. So really, D doesn't seem like it could be the answer, because it looks like this approaches 3 from the left, but this looks like it's approaching 3 from the right, or approaching 4 from the right. But from the right, this doesn't look like this is approaching 4. So yeah, so this is D. So that can't be a jump discontinuity if the y values look like they're approaching the same value from the left and right, which in this case is 3. Okay, next one, they give you a piecewise function. They also give you a graph of that piecewise function. See which one, maybe we'll use one or both or neither, or yeah, one or both. So they say let f be the piecewise function defined above. Also shown is a portion of the graph of f. What's the value of limit as x approaches 2 of f of x? Okay, so this is a composite function. So we're looking at limit approaches 2 of f of x. Okay, one property of limits for composite functions is you can take this limit and apply it into the inside of this. So we'll kind of rewrite this outside f. I'll do brackets. And then now we'll really just bring this limit inside and apply it just to the inside f. So this will be like limit x approaches 2 of the inside f. Okay, and the idea with this is we're going to basically like look at what this is approaching and maybe even just look at what this equals. And then whatever number this equals, we'll just do f of that number, and that'll basically be the answer. We'll see if there's anything tricky though. Okay, so limit as x approaches 2 of f of x. So as x approaches 2 from top and bottom, it approaches 5. So really this limit just equals 5. Okay, and then f of 5, we can't use this anymore because 5 doesn't show up. We can kind of estimate. It looks like among the answer choices, it looks like it might be 1/2 maybe, but let's see. So now we have to go up to that's why they give us the piecewise function. So f of 5, so here's f of x. So 5 is greater than 2, so we'll use the last piece. And then just plug in 5 into that. So 8 minus 3 over 2 times 5. Okay, that's what the graph looked like anyways. It looked like it was going to be a half. Okay, so yeah, so big thing to learn is when you have a limit of a composite function like this, you can bring the limit, this limit you can apply to the inside, evaluate the inside. There are certain tricky ones, you got to be careful. But for the most part, you'll evaluate the inside limit and then get a number and then just do the outside function of that number, just evaluating. Okay, next one, number 9. Okay, so let's look at this one. This is kind of a weird one. Okay, so give you a table, selected values, but they also give you the graph. Okay, the table above gives selected values for a function f. Also shown as a portion of the graph of f. The graph consists of a line segment for x less than 3, this decreasing line segment, and part of a parabola for x is greater than 3. Okay, what's the limit as x approaches 3 of f of x, at least among these answer choices? So, okay, so if you look at like when x is approaching 3 from the left, That would be like those values approaching 3 from the left. It looks like the function's approaching something around 1.6 or something, maybe, I don't know, maybe a little bit more, a little bit less, something like that. So let's just focus on that. So that's the function approaching 3 from the left. Okay, so let's look at this. So that's really just this piece right here. That piece is approaching 3 from the left. So this is really more of like just noticing that you're dealing with a decreasing function. So notice like this function's decreasing, 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 right? So notice that like at 2.99, so it's some value really close to 3, but less than, the function equals 1.601. But notice this function's decreasing. So as you get closer to 3, you're going to get y values a little smaller than this, right? These y values are actually decreasing. So if you go even farther, closer to 3 from the left, the y values are going to get smaller than this. So, so the limit as x approaches 3, as we get closer and closer to 3, can't be bigger than this since the function is decreasing. So it has to be like maybe 1.6. Has to be just a little bit less than that. So it can't be 1.602 because that's greater. So it just has to be just 1.6. Okay, next one. Okay, function f is defined above. Which of the following statements is true? So this is another one where they define f as a certain function when x doesn't equal a number, and then bottom thing, when x equals 2, the function equals 7. This is just the 0.2 comma 7. Okay, which of the following statements is true? Let's just look at all the statements first. Maybe f is continuous, maybe it has a removable discontinuity, a jump continuity, or a vertical asymptote. So notice these are all just the 3 types of discontinuity, or it's continuous. So let's just see what's going on at 2. Okay, so when this says the function equals this when x doesn't equal 2, so really the function will equal this from the left and right. Okay, so let's look at, if we look at limit as x approaches 2, and that'll be from the left or right. Okay, first thing is just directly substitute. If you plug in 2, you get 8 minus 6 minus 2, that's 0, and the bottom is 0. Okay. Okay, little tip with these rational functions. If 2 makes a polynomial 0, then x minus 2 has to be a factor. So we can look at the top and just know x minus 2 is a factor. And then, if you think about it, you need x to get multiplied by this first term in the binomial to get 2x squared. So this term has to be 2x. The first term in that second binomial has to be 2x. Okay, and then to get this negative 2, you have to do this number times this number. So negative 2 times 1 would give you that negative 2. So this has to be a plus 1. And then you could even FOIL just to make sure that the middle term ends up being negative 3x, but in this case it does, because these multiply, the inner ones multiply to be negative 4x, and the outer ones multiply to be a positive x, and those combine to be negative 3x, so that works. Okay, so we know with rational functions we can factor the top and bottom if we get 0 over 0, and then cancel out the same factor, and then replug in the limit. So if you replug in that limit, and plug in 2 into 2x minus or plus 1, you get 5. So limit as x approaches 2 equals 5, which doesn't equal f of 2, right? According to this, f of 2 equals 7. So that doesn't equal f of 2 because that's 7. So that means it's not continuous. But it equals 5 from the left and right. So it equals the same value from the left and right, but it doesn't equal the function at that value, and that's a removable discontinuity. So I don't know exactly what this function looks like. Actually, we do. It's 2x plus 1. So if we graphed it just to see what's going on, this function would look, it would have a hole at 2, 5. But besides that, it would just be some linear function, actually. Okay, and then if this is 5, and then this up here was 7, it would have a point at 2, 7. So that's what this function looks like, this piecewise function. So we can see there's a hole right there. Okay, next one. The function f has a jump discontinuity at x equals 3, which is the following as a graph at f. So boom, right there. So that's removable at 3. That's not even discontinuous at 3. That's continuous. There's a jump, and there's an infinite. So this is just recognizing graphs. Okay, number 12. They say the graph of a function f is shown in the figure above. At what value of x does f have a removable discontinuity? All right, so removable discontinuity is not, so this is an open circle at an endpoint, which is different than this which is really a hole. Yeah, so this at x equals 1, that's a jump discontinuity, but at x equals 3, that's a hole. That's a removable discontinuity. So the answer is B, x equals 3. And just realize, you know, these are both circles, you know, on the graph, but they're totally different things. This is an open circle at an endpoint, and this is a hole in a graph. Not totally different things, but different things. Okay, next question, number 13. If limit as x approaches 6 of f of x exists, with limit, excuse me, as x approaches 6 of f of x being less than 5, whatever this limit is, it's less than 5, and f of 6 equals 10, which of the following statements must be false? Okay, so limit as x approaches 6 is some number less than 5, so this limit's approaching 4 or 3 or 2. This limit as x approaches 6 is approaching a number less than 5, but f of 6 equals a number bigger than 5, which of the following statements must be true? Okay, let's just look at the answer choices. Okay, and they also keep in mind they say limit exists. Okay, so think about, let's just kind of, we'll graph it just to see, and that's kind of what I'm doing in my head anyways. So let's look at x equals 6, and let's say this is 5. Okay, one thing they say f of 6 is 10, let's just give a point right there. So 6 comma 10. But besides that, they say the function is always, the limit as x approaches 6 is whatever it is, it's less than 5, but it exists. They say the limit exists, but it's less than 5. So the only kind of option is it kind of does something here. It could go up or down. So notice the limit as x approaches 6 exists and is less than 5, but then you have this random point above here. So let's look at all the answer choices. Does limit as x approaches 6 from the left have to equal 0? No, it could equal anything, but just something less than 5. Does limit as x approaches 6 from the right have to be less than 5? Yeah, for sure. Right, because the limit from both sides have to be less than 5. So this next one, then we're seeing which ones must be false. Okay, so really this doesn't have to be false. This could be true. I should have said that. This is less than 5, and that Doesn't have to be false, doesn't must be false. So that's not an answer choice. Okay, this doesn't have to be false because this is actually always true. Same with this one. This has to be true in order for the limit to exist. So which of the following must be false? It must be false that it's not continuous, that it's continuous at x equals 6. This has to be false because we know the function has to have a hole because the limit approaches some number that couldn't possibly be the function, the value of the function. So we know whatever the limit is of this function, it can't equal f of, as x approaches 6, it can't equal f of 6 because this is smaller than this. So these can't be equal. Okay, and that means it can't be continuous. That means this has to be false. Okay, number 14. Let f be the function defined above. Which of the following statements is true? Okay, they all talk about either f is continuous or it's not continuous for some reason. So let's first figure out if it's continuous or not. Okay, so let's see. So we look at kind of 1 is like a boundary point of this piecewise function. So let's basically plug in 1 by, in order to look at the limits. So let's say we do limit so x approaches 1 from the left. Okay, from the left is values less than 1, so we'll plug in 1 into that, and we get 2. The limit as x approaches 1 from the right, f of x. Okay, from the right is from values greater than 1, so plug in 1 into that. We get a half minus 1, which is negative a half, plus 5 is 4 halves, which is 2. Okay, so they equal each other from the right and left, but notice there's no equal 1 here or equal 1 here. It's just x is greater than 1 and x is less than 1. So this function we know is discontinuous at 1 because there's 1 isn't even in the domain, right? This is the domain of piecewise functions, and there's no equals 1 here, so this function never doesn't have a point for x equals 1. So we know it's not continuous at 1, so we knew right away it's not A. But we also know it doesn't exist at 1, but from the left and right of 1, it equals the same value. And so really this is the only reason why it's not continuous. So this isn't true. We know that this is, these two limits do equal each other because they both equal 2, so this is not true. And then they say the limit doesn't exist. No, it exists because it equals the same thing from the left and right, so it's not that, not that. It's not continuous, and so B is the answer. So it does exist, or it's not continuous, and that's just because f of 1 doesn't exist. That's the only reason. Okay, last one, number 15, they say, which of the following functions is continuous at x equals 3? Okay, so really, for this one, we just have to really plug in 3 into the simplified version. Actually, let's look at this. So if you plug in 3 into the top, you get 9 plus 3 is 12, minus 12 is 0, and then 0 on the bottom, so you get 0 over 0. But then we cancel. So let's look at this. So if you factor the top, I'll kind of do this one a little quicker. I'll do this one as quick as I would do it if I was doing this problem. Okay, so we're really just going to factor the top. So we know that x minus 3 is a factor. That'll be x plus 4. Out, and then now plug in 3 into this and you get 7. Okay, but you should get the same thing, but you don't, so it's not this one. Okay, do the next one. So plug in 3 here. Well, which of the following function is continuous? It can't be this one. If it's not even defined at 3, it can't be continuous at 3. So we don't even have to test the outside ones. Okay. Okay, so let's do this one. We'll plug in 3 into this one and this one. Okay, plug in 3 into the top one. You get -8 sine of 3 pi over 2. Okay, sine of 3 pi over 2 is -1. That's 8. Okay, so that's looking good. So that x at 3 equals 8, and this limit as x approaches 3 from the left is 8. So that's good. So if we plug in 3 into this one and it equals 8, then that's going to be the answer, because that'll make all 3 of these equal from the left, from the right, and at 3. If they all equal each other, then it's continuous. So let's plug it into the bottom. So plug in 3 in for x, you get 3 pi. Okay, and then cosine 3 pi is the same as cosine pi, which is -1. So that works. Okay, so this is limit as x approaches 3 from the left, limit as x approaches 3 from the right. Those are equal, and they equal what the function equals at 3. So that means the function is continuous. Oops. At x equals 3 for that one.